Okay, you can start it now.
Okay, today we're going to solve a graph problem called cheapest flights within K stops. And so we're given n cities connected by some number of flights. N are the nodes of the graph. So 1, 2, 1, 0, 1, 2, 3. And we're given an array of flights, a list of lists, where we have a from, a to, and a price. So we want to find the cheapest way to get from the source node to the destination node, not stopping more than K times. And if there's no such route, then return -1. So you can do this either using Dijkstra's algorithm or Bellman-Ford's algorithm. We're going to use Bellman-Ford's algorithm because that's just the way I know how to do it, because it's one of the two ways to get the shortest path. So cool, we're going to do this using iteration in a way where we're going to use infinity, and we're just going to try different flights and see which one is the cheapest. So let's declare an array called prices. Initialize every single city to have a cost of infinity initially, because it's going to be updated later. And then set the source node to have 0 cost, because we're already starting at the source node, so there's no cost to get there, right? So notice that our constraint here is K stops. So we're going to iterate K times. As soon as we break this constraint, then the whole problem's over. We have to return whatever we have. Whether we can reach that destination at all, or if we do, then the cheapest price. So let's create a temporary array, because we don't want to prematurely mess up the prices array if we didn't finish the current flight yet. So let's create a copy, and now we can iterate through our flight. So we're on the first node now. We're going to decide which flight do we take. So source, destination, price, because from is basically the source, to is the destination, and price is the price. So for all this in flights, if we're seeing infinity, then we can't even reach that flight because the cost is too much, right? We don't have infinity number of dollars. If that's not the case, then we can reach it. And so we're going to ask the question whether we found a cheaper path to get to our whatever node previous to the current. So if prices S plus P is less than TMPD, because TMP is already the prices array, then we're going to update it to the cheaper price. And now we can, because we finished the entire flight, so we actually know, aka we iterated through every single sublist in the input list, then we now know which one's going to be our best option. So before we couldn't update, now we can update our prices array to become TMP. And again, our constraint is K, so after we stop K times, we're done, the game's over. So at that point, either we did reach our destination or we didn't. So if we didn't reach our destination, we're still seeing infinity there because it didn't get updated at all, and we're going to skip it here. Then we can just return -1, as said right there, meaning there's no such route to get to the destination. If that's not the case, then whatever is in our prices at the destination node is going to be our best answer. So we're just going to return prices DST. And yeah, that's it. So let's run this. As you can see, it passes all test cases.
Okay.
And then let's submit it.
Now let's see.
And yeah,
Ooh.
There you go.
Wow.
Time complexity is O of n times f, if you want to say that, because we have to iterate through 2 arrays. Yeah. However long, it's O of k times f, because k could be really, really big. You could have a really big allowance, and then flights could also be really big. And the space complexity is going to be O of n, because we have 2 arrays here that we're using to store our result, so we don't prematurely update. Yes. We don't get incorrect results.
So I think the time capacity of your program is k power n, k power to n, right?
To f, whatever you want to call it. Yeah.
Yeah, F. Yeah. Okay, it's good.